Okay. Good morning, my dear students. Good morning. Nice to meet you all today morning. Yeah? Nice to meet you. Good morning. Nice. So for today's discussion, I will project this one. Right. Last class, I was doing this problem. Two-way slab but restrained. Okay. Actually, when we were studying, we studied a working stress method. That time we were beginner. No, 30 years back I studied. That time you see, you not even 35 years back almost. At that time, what we referred this one reinforced concrete design by S. Ramamridam. Okay, that working stress method we referred. In that this design of one-way slab, two-way slab, corners held down, corners not held down, and all nicely discussed. Okay, nice. We have learned it very thoroughly. But in limited design approach, that book, okay, I am referring one standard book written by IIT professor and former HOD of IIT Chennai, Professor P.C. Varghese. His book I am referring, almost the same standard. Okay, it is written by IIT professor. Obviously, whatever the subject which I am teaching, I am referring a textbook written by IIT professor. I am teaching from that book. His notes, Abdina, it is almost standard teaching. Okay, standard notes of an IIT professor. So you are no way lower than IIT. The teaching is being done. Okay, and not no way lower than IIT, on par with that standard we have been teaching you. Because I am referring a textbook written by a former professor of IIT Chennai. Remember that, keep it in mind. That is the standard of teaching we do. That's what I want to tell you, because we refer IIT notes. Okay, and we have been teaching here. Very good. So this corners held down I was doing in the last class, right? So here I've off problem I completed. So we have seen how to compute bending moment along short direction and long direction. At along short direction, you got three moments. At three places you got moment. What are the places? Mid span. Okay, they are positive moment, and a negative moment at edges. Okay, one edge is continuous edge, another one is discontinuous edge. Okay, in continuous edge you got a moment almost 4/3 of the positive moment. Keep it in mind. There are thumb rule. Okay, at discontinuous edge you got a moment slightly below or at least equal to half of positive moment. Okay, so the determination of that positive moment is very important. Once you know the positive moment at midspan, positive moment in that kind of beams, kind of slabs, you can get the bending moment at a continuous edge, which is 4/3. Okay, 4/3 of the positive moment, and at a discontinuous edge, of 1/2 of positive moment. Okay, this is the thumb rule. So you got, but we referred bending moment coefficient and computed, and it is realized. That's why the note the author has given moment, the negative moment 4/3. Okay, 4/3 of m of positive, or at a continuous edge, and 1/2 m of positive, or at a discontinuous edge. He said. So even you can use this rule also to determine the area still required. Otherwise, moment induced in those edges. Okay, that's what. So you got three moments here along short direction. Along long direction also, the similar way we got three moments. One at a positive bending moment at midspan, and a negative bending moment at a continuous edge, and a negative moment at a discontinuous edge. Okay, so totally 6 moments we have got. So you have to design reinforcement for all these 6 moments. Okay. Next, this can be written later also, but the author written here. What should be the reinforcement in edge strip? At the edge strip also you have to provide a bending moment. Reinforcement, because at edge strip you have hogging bending moment. Okay, along this edge, called edge strip, some length. What length we will see? Might be maybe 0.1 LX. Okay, or let us see 0.1 LX or 0.2 LX maybe. Might be 0.2 LX. Okay, 5 meter now, at least 1 meter wide strip you have to provide that reinforcement. Now you will be providing crank bend up bar or a top gauge you can provide. Okay, and also longitudinal long span direction as well as the short span direction. You have to provide reinforcement gauge called reinforcement in edge strip. That you can provide the minimum. Okay, that's what. What is the minimum reinforcement to be provided in slab? 0.12%. Okay, 0.12% by 100 into BD. B is 1000, D H, grass area. 0.12% grass area, not effective area. 0.12% grass area na 0.12 by 100 into B is 1000 into H, BH. Okay, the total thickness of the slab. In this problem, it is 180 mm. Okay, please remember, since the slab thickness is 180 mm, the author has used 12 mm diabar. That is right only. When the slab thickness is 180 mm or 200 mm thick, such a high thickness is more, no, nothing wrong in using 12 mm diabars in this slab. That is the reason the author preferred to use it. Okay, but normally when you do slab design, mostly your thickness of the slab will not exceed 150 or 160. Okay, it is preferable to use only 10 mm or 8 mm in your slab. That's what I told you. So the minimum reinforcement is 1 to be 216 mm square. Okay, the spacing should not exceed 3D or 300 mm, whichever is less. Obviously, it's going to be 300 mm less. Okay, 300 mm. The spacing should not exceed 300 mm. Okay, so but still he has not provided that. He has discussed in the latter stage. This can be this reinforcement in edge strip can be done later also. No problem. Only area of steel required he determined at the edge strips. Okay, now straight away the author has gone to tabulation. Okay, so you rule out a table like this. Nicely, he ruled out a table. Okay, to do the computation. Nice one. Actually, this problem is a lengthy problem. Okay, comparatively lengthy problem. The examination chances are there to ask or not. I cannot assure you. It depends on, okay, because lengthy problem, it will consume more of time, more than 20 minutes it will, okay. But if you practice well, any problem, whatever lengthy it is, you can do it within 15 minutes or 20 minutes, provided if you practice it well, right? If you are very thorough in this subject and practice well. Because during my college days, I have done like that only. Whatever problem given, whatever lengthy it is, since I practiced, I used to do it within the available time, 20 minutes or 15 minutes for a problem, right? So here in the tabulation, bending moment is given, bending moment BM. Okay, M in 10 to the power of 6 because they are in a kilonewton meter. That's why in 10 to the power of 6 is written in order to convert that into Newton mm. Okay, short span, hogging bending moment. Okay, negative bending moment at a continuous edge, and then positive bending moment at a mid span. Negative bending moment at a discontinuous edge written, and then long span. Already we have determined, no, negative bending moment at a continuous edge, positive bending moment at a mid span, negative moment at a discontinuous edge. All moments are written. Okay, so they have computed M by BD square parameter. Okay, because you cannot do it in a calculative way. That formula, because that formula you will be getting quadratic equation. No, annex the formula which is available in annex G. You cannot, you may not prefer to use it because for all the 6 you will be getting a quadratic equation. You got to solve it. Solving 6 quadratic equation is going to be time consumable and lengthy, obviously. So the brilliant way is referring the SP16. Okay, so the author has referred SP16. That is why he has computed M by BD square, right? So M by BD square parameter is computed. These are the parameter, M by BD square value he has written, right? Then the percentage of steel. So referred SP16 table 4, okay, of SP16. Why? Is it M25 grade concrete? Yes, of course. You know, because several times you have seen how to refer M by BD square, how to, for a 415 steel, how to get a percentage of steel, okay, for reinforcement percentage, PT for singly reinforced section, okay. This table 4 of IS 456 for FCK 30, no, maybe table 3. The FCK is 25. Yours is 25 or 20? Whatever it is, let us see in that problem, okay. Which table you are supposed to refer? What is the area grade of concrete given? 20 or 25 in the problem? Let us go. M20 only. Okay, it's 20 grade concrete, right, in this problem. So you have to refer which table of SP16. This is for FCK 20, table 2. Table 2 you have to refer for 415 grade steel for the M by BD square computer. You have to take it approximately. You do not do Paka interpolation. If you know the procedure of doing Paka interpolation for single beam design, you can do. But there are 6 times you have to take percentage of steel. No, roughly you take. Suppose your M by BD square value lies somewhere between this, whether it may lie exactly at the middle or 1/4 or 3/4. You see, accordingly you take the value. Okay, either half middle of the average of this one you have to go middle na, 1/4, you know how to take it. Okay, between these two value, approximately you guess and write down. Okay, during exam, right? That's what percentage of steel written. And then what is the area of steel required? Once you know the percentage, area of steel equal to percentage of steel, the percentage of steel into BD by 100, isn't it? Using this, you can compute area of steel required. Okay, this much mm square, this much mm square. Okay, like that, area of steel required at those locations in this slab. Okay, along shorter span direction, at mid span, at a continuous edge, at a discontinuous edge. Along long span, at a continuous edge, okay, at a mid span, at a discontinuous edge. What is the area of steel required? You compute it. So the author preferred to use 20 mm dia bar. I told you, since the thickness happened to be 180 mm. Okay, that is why T12 he has written. It means tar steel 12. Fe415 steel is a tar steel. Okay, that's why T12 at 200 mm center to center. He determined the spacing required. This and all already you are familiar. Every time I cannot teach you. Okay, the design of singly reinforced beam, you have learned very well how to determine spacing. Once you know the area of steel required, how to determine the spacing required for 1 meter wide strip, that is 1000 mm wide strip. That you know how to get it. Okay, for that the area of steel provided is 566. Area of steel required is 520 mm square. Always the provided should be slightly higher than the required. Okay, 566. And then positive bending moment midspan of the along short direction, T12 at 275. Next one, the T12 at 275. So what is the area of steel provided? Also he has written. See, they are slightly more than the required one. These are the required area of steel required. These are the area of steel provided. Okay, so this way. And then long span direction also, you use 12 mm dia bar, T12 at 275 mm center to center. Okay, 285 mm square is the area of steel provided. See, have a look. This and all, you are the decision maker. Okay, what should be the, suppose you are using 10 or I don't want to use 12, I am using only 10 mm dia bar, nothing wrong. You can use T10. Accordingly, you will be getting spacing. Okay, everywhere you have to follow the procedure, but you do not take it too accurate. Approximately you can provide it. Okay, just you compute and okay, I want to provide this much spacing. Okay. But see here, practically applying them on field, there are difficulties involved. It is easy to compute. You can tell. See, just to think over, in a slab at along short span direction, at mid span, the spacing between the reinforcement should be 200 mm. When it comes to continuous edge and discontinuous edge, the author has said 270 mm spacing. Okay, how to provide it? This and all is art of detailing. In the field, even in the drawing, when you do design and drawing, the drawing or the architect, when they do drawing, they will do it, curtailment of bars and putting extra pieces of bars, introducing extra pieces of bar in between. Likewise, it will be adjusted during in the construction. Okay, I hope you will understand what I am trying to tell you, right? Because you cannot provide one bar continuously from one end to other end of the slab, because the spacing required differ at midspan, at edges. Okay, at the continuous edge, at discontinuous edge. How to provide it? The positive bending moment you have to curtail. Okay, alternative bars can be curtailed. Here the spacing is maintained 200 mm at midspan. At a negative, at a continuous edge, I want more spacing, so I can cut certain alternative bars, or I can introduce something. You have to do it, and you have to see that the area is area of steel provided. Unless we should not provide more steel, uneconomical. We are spending because we are buying steel and using it in our structure. No, so nobody prefer to use spend more. So what is required? That only we provide economical. Safety also should be ensured. Economy also should be kept in mind. Okay, both the safety and the economy, both are to be kept in mind. And for that purpose only we do all design and all. Very good. Long span also as provided. Just have a look. But it's a lengthy. It is tabulated and said. But doing calculation and computation and all, it's a lengthy process. Okay, to finish this table, how much time it will consume? Think about it, right? So this way, but you should know the procedure. That's why I'm teaching you. Whether the examination can you able capable of doing or not, you can do if you provided if you practice it well. Okay, but just I am telling a note. Some note has been written. That's what I have shown in chapter 4. The value of percentage increases more than. Okay, hence the area of steel. That's what is written. The area of steel at the conduit support is slightly larger than 4/3, and at a discontinuous edge slightly less than 1/2 of the steel at midspan. Okay, selection of midspan steel should be made by taking note of this fact. Okay, that's what design of positive bending movement. Midspan steel is important. Once you know that, you can follow this thumb rule and determine the steel at other places apart from this doing this calculation and all. No problem. That's what. Now he has come to reinforcement at the edge strip. Already we calculated the area of steel required at edge strip. No, yeah, it's here. Now he has computed the area of steel required at edge strip. Already we had computed. It's written. So the author used 10 mm diabar at a maximum spacing 300 mm. It has got it. For that, the area of steel provided is 262 mm square per meter run. Okay, in 1 meter wide strip. Per meter now 1 meter wide for 1 meter wide strip. Okay, per meter means what? 1 meter wide beam. The slab we were treating as 1 meter wide strip. No beam. No, that what. In that, the area of steel provided is 262 mm square. Okay, this 262 mm square is not for the entire whole slab. Only for 1 meter wide width of the slab. Keep it in mind. Everything we are discussing unit width of the slab. That you keep it in mind. Okay, the area of steel is required and the edge strip is area of steel and all we will see, right? And then corner steel, full corner steel. Full corner steel has used 0.75 maximum positive steel. 75% of the positive steel he has taken. Author has taken. Okay, where is the provision in the IS code and all not mentioned here? No problem. Corner steel, you are going to do some bend up bars. Crank you can provide, or some corner you have to take some pieces of bars you can put in your own. Okay, that's what T10 to 270 mm standard center. See, you should know the theory, but in practice we will not stick too much onto the theory. Okay, you should not stick too much onto the theory in practice. What to do? But you should keep it in mind. If the corners are held down, at the corners there are going to be torsional moment. Tension will be there at the top. Tension cracks will form at the top. I have to prevent it. For that, I have to provide a reinforcement cage at the top. Maybe 0.2 meter. 0.2 times the span. 0.2 times the span. 5 meter span. No, never problem. So 1 meter. 1 meter this side. Here 0.2 times 8.75 meter. No, 0.2 times 8.7 meter. That much width. I have to provide the torsional steel. You can provide some 10 mm diabar, 8 mm diabar at some spacing. As we mentioned here, 250 mm spacing you can provide, or 200 mm spacing you can provide. No problem. Okay. Some calculation also have to do, and you have to do it. That's what. Almost you completed the design, right? Now you have to check for deflection. Deflection, actually we started with deflection. Serviceability requirement we are going to check. So far in strength aspects we have completed the design. But we started with to determine thickness of slab, we started with that one only. Which one? The span to effective depth ratio. There itself, the serviceability requirement of deflection is taken care. Okay. Again, you have to recheck. Again, you determine what is the actual span provided divided by span to effective depth ratio. Okay. You just compute and say, tell it lies between 25 to 40. No problem. Okay. Hence, okay. The limit set of deflection is okay. Next, cracking. Cracking, what is that? The spacing should the minimum percentage of reinforcement should have been provided. That you have provided. How much? 0.12% of the grass area of the slab. That we have provided, no doubt. 0.12%, more than 0.12% of grass area still provided. One requirement is over. What is the next requirement in cracking point of view? Limiting cracking point of view. The spacing should not exceed 300 mm. 3D or 300 mm, whichever is less. So 300 mm is going to be less. Okay, so the spacing provided is okay. And then the diameter of the bar used should not be more than 1/8 of the thickness of the slab. That is missing here. That also I have to show. Yes, the diameter of the bar used is less than 1/8 of the thickness of the slab. Here the thickness of slab is 180 mm. 180 by 8, okay? It should be less than that. That check why the author has not done, because okay, you check it later. That check and all to be satisfied. Hence, limit state of cracking, okay. And then arrangement of steel, details steel according to the standard practice. Details steel according to the standard practice. That's all. It completed. How to do one? Okay, with this this unit is over. This is two problem only. In a design of two-way slabs, we have discussed only two problem. One is corners edges are simply supported, corners are not held down. Another case, there are some continuous edge, there are some discontinuous edge, okay, and the corners are held down. This two problem only we have seen. And how to details are in a usual manner, that is art. You have to take any textbook and observe and learn in your own. Okay, there are plenty of textbooks available. Plenty means PC Varghese is a book I am suggesting. Okay, and PC Punmiya is there. Ashok Jain, Kumar Jain, PC Punmiya. Actually, when I was studying in limit state design, the only Andinathar book available was Ashok Kumar Jain. Limit state design by Ashok Kumar Jain. Okay, now the textbook is written by PC Punmiya, Ashok Kumar Jain, and Arun Kumar Jain. That book is available, Indian author book. Okay, the another good book. And there are some other books like written by IIT professor Devdas Menon and Pillai. Okay, those books also you can refer drawings. But here, this book I found the drawings are neatly given. Just you observe it. I will show you how to detail it. We have done seen design so far, but how to detail? The examination time will not be there. No, next semester you have design and drawing. That time you have to draw all these drawings. Okay, this is the detailing. Actually, the book. Can I do this one? Which one? View, rotate view. I will just rotate it for you. Oh, this cannot be rotated. It's a PDF file. Why it's rotating? Oh, rotating possible. Clockwise. Yeah, now it's visible. Very good. So I will reduce the percentage to 150. You can see it fully. Yeah, now it's available. Very good. See here. How to provide it, right? Reinforcement drawing for two-way restrained slabs. Okay. Reinforcement drawing for two-way restrained slab. Is it top and bottom plan combined using straight bars? This is bottom one. Okay. Top and bottom plan combined is written. And here is one top plan. Okay, this top plan is here. Yeah. Okay. This is bottom one. Yeah, it's the bottom. This is the bottom plan. See here, you have along short span direction, bar is shown. Okay, the bar is extended to up to the end, alternate bar. Here, see the bar is curtailed here. The bar is not fully taken up to this, curtailed, because here more spacing required, here comparatively lesser spacing required. No, that is why. That's why, see this bar is curtailed. It's not taken up to the end. And you have to do that, and then they put some dot and put some arrow, means it is extended up to the here, spacing. At this spacing, these bars are extended. You need not draw all the bar. Only true bar, if you show it in your drawing, is sufficient. This is a way of doing. And you have to put some dot, and you have to draw the line and show the arrow light. This should be thick. Okay, the bar should be thick in your drawing, and this arrow should be thin, very thin and light in your drawing and shown. Okay, it means they are placed at required spacing. Okay, and you have to write the spacing and all. Here itself you can give the designation that I told you, abbreviated manner you have to write, or at the bottom also you can show it. Okay, but design and drawing you will be showing adjustment to that, putting arrow mark. Okay, T10, T12 at 200 mm center to center, you will be writing. Okay, the bar detailing. And then see here, in long span direction also, the bar is shown. This bar starts from here, goes here and curtailed. This bar comes here and curtailed. It means here the spacing will be more. Here the spacing will be more, okay, because you are curtailing the bar. Alternate bars are curtailed. Here the spacing is less. So 200 mm spacing, here I have required only 275 mm spacing. That will be adjusted. Suppose the spacing 275, but it exceeds. What is the site engineer will do? He will take extra pieces of bars. Need not be the same 12 mm dia bar, sometimes 8 mm dia bar. Because if you put a 12 mm dia bar introduced in between, the area of steel will be may go high. That is why he will take a 10 mm dia bar piece or 8 mm dia bar piece and he will introduce in between the bar. Whether you are getting it or not. See, all of you see here. Suppose you take this way, the spacing is only 200 mm. We have seen just now the calculation. No, the spacing is 200 mm center to center. I have curtailed bars, alternate bars. Okay, so the next bar introduced here will come to up to this. Okay, we'll hope you will understand now. Come up to this. Now, what is the spacing between the bar? 200, another 200, 400 mm spacing. But in the calculation, 275 mm spacing is supposed to be. But it comes around 400 mm spacing. Now the area of steel provided reduced. Okay, how do I compensate it? I cannot introduce another 12 mm wire in between. Again, whatever area of steel provided, same area of steel will come here. Okay, so in between these two 12 mm dia bar, okay, this author has used 12 mm dia bar. That's why I'm telling. In between this 200 mm dia bar, which are spaced at 400 mm, I can introduce in between some 10 mm dia bar or 8 mm dia bar. So my area of steel provided for 1 meter wide, for 1 meter length, for unit length, will be the computed one. The area of steel required there in that locality. Okay, this way it's an art. Either the architect who draw the drawing should decide, but everything he cannot show. But okay, simply he will show something and will tell. But the site engineer should take care. He also should be highly knowledgeable in the structural design. Accordingly, he has to refer the drawing. How much area of steel required? Okay, this much. Whether 1 meter wide, whether that much area of steel I am accommodating or not. Then he has to put some pieces of bars there. Okay, maybe it is given here. See, Lx by 5. Lx by 5, it should be spread to a length of Lx by 5 means 0.2 times Lx. I told you no. That is 0.2. Here it is 5 meter for 1 meter width. Okay, provided. See, sit and keenly observe this drawing letter. Okay, now I cannot tell you everything. You have to spend more time on this kind of subject and take the drawing and keenly observe. You will learn it. Okay, I advise you to go through it. And then the edge strip steels are provided. How the edge strip steels are shown here. Okay, the edge strip steel provided in the long span direction as well as short span direction. Edge strip steels are to be provided. Okay, and this torsion corner steel is provided here, right? How it is provided? See here, 0.2 times this direction. Okay, that is Lx by 5, Ly by 5 distance. You have to provide the torsion steel at corner, called the torsion steel or corner steel. Okay, no, here in this drawing you are seeing bottom steel at the bottom of slab. This is the reinforcement detail for bottom of the slab. So that at the top of the slab, the detail is here. Okay, at top of the slab, edge strip steel line, edge strip steel, how it is provided, how this torsion steel is provided at top of the slab. Okay, this is top reinforcement details view. Okay, please see it, go through. But the presentation may differ from textbook to textbook. Okay, or even in the net you can download many design and drawing. You can see the detailing of a two-way slab images. You can download from net. You are living in a wonderful time. No, there's a powerful tool in front of us, the internet. In that you can download many drawing. Okay, the structural drawing. In that you can observe how it is presented. The way of presentation differ from country to country. That the designation I told you. No, this author used T10 at 120. That's all. In some book you see they might use some asterisk. Some people use circle and some T in that to represent raw steel. They put some T and then circle it. Okay, that kind of notation also is used to represent raw steel. This author used only capital T to represent raw steel. Some book you can see only asterisk to represent raw steel. Likewise, the way of designation with some differences are there. Okay, everything is right legally speaking. Okay, because it is there in drawing. But you have to see in practice in our locally how the drawings are being prepared, how the designations are being done. All you should have to observe. Okay, through some source. I advise you to do it, right? That's what, top still. Today I thought of starting even a design of short column. Okay, with this unit is over. Your third unit is over with this. Okay, just see, the notes is there for design of next time. I'm going to start next class. I thought of starting it today. Okay, I will start it in next class. Limit state of collapse in compression, design of axially loaded short column. Okay, it's a lengthy chapter. Okay, I have to take many number of classes to complete this unit. That is your fourth unit. Now I am going, next class I am going to start your fourth unit, design of columns. Okay, in that short column, axially loaded short column, and then short column only. But in addition to axial load, there are going to be bending movement. Okay, uniaxial bending, biaxial bending problem, and all we are going to see using interaction diagram how to design it. Okay, for that we are going to use a diagram called interaction diagram, like easy reading. Okay, there is a SP16. There are interaction diagram available. You are going to refer that to design, and then slender column. Okay, so the column design is very lengthy. Chapter column chapter is lengthy one. I require many number of classes to complete this one. Okay, so next class I will start this one. Since many of your students are attending implant training, they are not in a position to attend online class. However, the recorded video will be sent to them. I want to record your names of the student, those who are attending online class now today. Okay, the exemption is given for those who are attending. Nearly 50% of your classes are attending implant training. No, for them the recorded video will be sent. Okay, I will stop with this one. Just a few minutes. If you want to discuss anything, we will discuss. Okay, stop recording. Right.